Hey guys, here's the second day of 2.2, which was basic differentiation rules and rates of change. We're going to focus on looking at some examples today. So we went over the big ideas yesterday. Today is just a couple examples and one new rule, which we'll get to halfway through. Okay, so the first one, find the derivatives of the two functions. What do you notice? Why don't you go ahead and try this one on your own, hit pause, and then come on back. Okay, so the first function is going to give you a derivative of 6x, and the second function, g, is also going to give you a derivative of 6x. So this is kind of weird that these two functions are different, but have the same derivative. So is that okay? Well, think about it, what the graphs would look like. 3x squared plus 4. It's going to be the function 3x squared shifted up 4 units. Maybe we can plot 1 point on either side. If we sub a 1 in, we're going to get a 7. Okay, let's connect those dots. And we get f. Well, what does g look like? G is the function shifted down a unit. Okay, so g is going to be down here. If we sub a 1 on either side, we'll get a 2 out, and we get this function. So they're very similar functions. Just one is shifted up and one is shifted down. So what we said were these were the same derivatives. So what we're saying is at any given x, they will have the same rate of change. Let's see if that makes sense. Okay, one thing I want you to notice looking at this is find out where the derivative is 0, which means a horizontal tangent line. Do you see that right there? And then look at also right here. So at x equals 0, we have horizontal tangent lines for both functions. Also look at this. If you draw a tangent line here and a tangent line here, do you guys get that they have the same slope? Okay, so this is kind of just an observation to make. We can have different functions that have the same derivatives because at any given x, like the ones we just looked at, here and here, they have the same slope. Or if we look at 1 and 1. You could do the same thing and look at -1 and -1. You can see that they have the same rate of change. Okay, that was just kind of a neat problem. Let's go on to 2. Again, hit pause and try this on your own. I'm asking you to sketch the graph of a function f such that f prime is greater than 0. Well, what does f prime greater than 0 mean? That means f is increasing. So if f is increasing, let's make a note. Okay, that's what it means when f prime is positive. What does it mean, the rate of change of the function? So what is that saying, the rate of change of the function? Isn't that just the derivative? So instead of saying the rate of change of the function, we can say f prime is increasing. Okay, so we're trying to decode what this says so we know how to make this graph. What does it mean if f prime is increasing? Okay, so what's another word for f prime? We could think of that as the slope of the tangent. Okay, so if the slopes of the tangents, if those values are increasing, what does that mean? That's going to mean the tangent lines get steeper. Again, if you need me to say that again, if f prime is increasing, that means the slopes are getting bigger. Well, here's a relatively flat slope. Here's a bigger positive slope and even a bigger one. So our tangent lines, if you saw, they got steeper. So I need a function who is increasing and whose tangent lines get steeper. So I'm going to go ahead and draw something. If you guys didn't already, if you could pause it and try it. So I need to move in this general direction. I have to be increasing. It does not have to be linear. I'm just saying if we start here, we have to end here, okay? And I need the tangent lines to get steeper. So here's what I'm thinking. In general, look, doesn't the function increase? Function's going up, and if you start drawing tangent lines in, actually let me use a color, you can see that they're getting steeper. Okay, next one. Find a and b such that f is differentiable everywhere. Well, remember the statement, to be differentiable, a function has to be continuous. If you look at these independent pieces, a line and a quadratic, those are continuous by themselves, but do they meet up at 1? Okay, so because it says we have to find a and b, we're going to force the continuity. So in order to force the continuity, we know that that means the limit as x approaches 1 from the left has to equal the limit as x approaches 1 from the right, which has to equal f of 1. Well, as we approach 1 from the left, we're going to use numbers less than 1, and we're going to use 3 minus x. So I'm going to have a 3 minus 1 here. 1 from the right, I'm going to use numbers greater than 1, so it's the bottom one, and I'm going to sub a 1 in for x. So 3 1 squared plus b times 1. Now I'm going to get 2 equals, and I see a little typo here. Let's fix this 3. That should be an a. Okay. Now we're not done because we have 2 letters here. We have A and B, and we have to figure out what those should be. But remember, they didn't say that they wanted f continuous. They said differentiable. We know that differentiability implies continuity. So we knew we could say this because in order for the differentiability to happen, we need continuity. Well, what does it mean to be differentiable? So let's check differentiability at x equals 1. That means the derivatives from the left and the right have to be the same. So what's the derivative from the left of 1? That's a negative 1. And then if I take this derivative, I'm going to get 2a plus b. So we're going to set the left derivative equal to the right derivative. Okay, but we did say at 1, so now let's look at 1, what happens. We're going to have negative 1 equals 2, a, x is 1 plus b. So negative 1 equals 2a plus b. So now I have this function. I have this equation and this equation. You can do whatever you want. I'm going to go ahead and I'm going to take this one over here, and I'm going to solve this for b. You could also use elimination, but I see a b here and I see a b here, so I think that'll be pretty quick. So b equals 2 minus a. Then I'm going to take negative 1 equals 2a plus. So what I'm doing now, again, I solved this for b and got b equals 2 minus a. Now I'm going to take this function and I'm going to replace this b right here with this new b. So it's going to be negative 1 equals 2a plus 2 minus a. If I combine like terms, I'm going to bring this 2 right here to the other side by subtracting it, and that's going to give me a negative 3, and then an a, so a is negative 3. But I'm not done because we also need b. But look I have this nice thing right here that says b is 2 minus a, so now I can say b is 2 minus negative 3, so b is 5. So now I have this b, and I have this a, and I know at these values the function will be differentiable, which also means continuous. Okay, so that was just a brush up of some stuff from the first day. Now we're going to go on to our new idea. We already learned the derivatives in general, and then we looked at sine and cosine. Today we're going to look at natural log. So first I wanted to remind you of these properties. Do you guys remember this? Natural log of 1 is 0, because there's really an e right here is like the base. So we could say e to the 0 is 1. That's why that works. So there's really no example to do over here. I'm just going to say natural log of 1 is 0. Here's a plus b. What this is saying is if these are multiplied, you're allowed to split it up separately as long as you have an addition in the middle. So let's try one of these. What if I gave you the natural log of 2x? What would that be? 2 and x are being multiplied, so it's natural log of 2 plus natural log of x. Okay, the next one is super similar, but now we're just dividing. So instead of adding, we're going to subtract now. So if I give you the natural log of x over 2, that's going to be the natural log of x minus the natural log of 2. Okay, the last one, if you have something to a power. So look, all we did here is this n is allowed to come down in front. So if you're taking the natural log of one thing to the power comes down in front. So our example will be, what if you have natural log of x to the 5th? You're allowed to write this as 5 natural log of x. Okay, guys, we're already halfway through. Okay, here's a review of pre-calc. So continuing what we just did, I'm asking you to expand these. So we have multiplication here. Multiplication breaks into addition. So this is going to be natural log of 5 plus natural log of x. Again, if you want to try these on your own, great idea. Next one, we have something to a power. In this case, we're allowed to bring that down in front, and you get 7 natural log of x. Okay, on the next one, this radical, I'm going to rewrite it as a minus 1 to the half. Now we're allowed to bring that down in front. Okay, this next one's going to take us a couple steps. We're dividing, so we have natural log of 1 minus natural log of xy. But look right here, we're going to keep going because xy is together. Also, natural log of 1, we know what that is. That was from the first page. We know that natural log of 1 is 0. Because remember, there's really a base e here. So what this question is saying is e to what power gives you 1? And e to the 0. So that's essentially gone. I have a negative. And then because in here I'm multiplying, I can break that up into addition. So it's natural log of x plus natural log of y. Okay, going on to the next one. Here, now we're going to learn the derivative. So the whole reason that I was reviewing these properties with you is we're going to need to use those when we take the derivative. So here's something for you guys to memorize. If you take the derivative, remember this is your operator, of the natural log of x, you are going to get 1 over x. Okay, so the derivative of natural log of x is going to be 1 over x. Remember, as long as x is positive. So let's just look at the graph real quick. I just want to remind you what this looks like. Natural log function looks like this. And this is the 0.10. Okay, 1 over x looks like this. And this is, again, just a sketch. It's coming down up here and doing this. Okay, so this green one is the derivative, and the pink one is our function. Okay, let's look at this for a second and just see if it makes sense. Notice that I did not draw any green over here, because if the pink function, which is our original function, doesn't exist here, how is it supposed to have a slope? Also, if you start drawing tangent lines in, tangent line here is super positive. That equates with a super positive number up here. Then it gets less positive, so it's still increasing, but at a slower rate. So a positive slope, but a smaller positive number. This function is always increasing. So that means if I go to graph the derivative output should always be above the x-axis, which they are. Also, this is starting to level off, so I'm getting close to 0 but positive, and this graph is getting close to 0 and positive. Okay, going on, if you're taking the derivatives involving logs, I want you to rewrite an expanded form first. So I want you to do what we were doing up above in example 4, and then go ahead and differentiate. Okay, so the first thing we're going to do on f is we'll just follow the directions and let's expand. Now, if 10 and x are being multiplied, we're going to break that out into natural log of 10 plus natural log of x. When I go to take the derivative, natural log of 10 would be a number. If we typed it in our calculator, we could find out what that is. That is just a number. And the derivative of a number is 0. The derivative of natural log of x, we learned up above that is just 1 over x. So this problem, even though natural logs seem confusing sometimes, is just 1 over x. Okay, going on to the next one. The biggest thing here, guys, is you only know how to take the derivative of natural log of x. So if they give you anything other than this at this point, we're going to have to break it apart so we just get natural log of x. Okay, so the first thing that we're going to do here is bring that 9 down. Now we have natural log of x, which means we can apply the derivative. So the derivative, 9 is a scalar. We write it in front. What's the derivative of natural log of x? It's 1 over x. And there's our derivative. Okay, going on to the next one. Oh, next and last. These are short today. Okay, first let's rewrite this. When we had a radical up above, we rewrote it as a half because it was the square root. Just like over here, when we brought the 9 down in front, I'm going to bring this half down in front. Notice I'm not writing, one thing, let me stop and point something out to you. This was the original function. This was the function. I did no calculus. I just split it up. Once I do calculus, then I write the f prime. Again, in this step, all I did was rewrite it, so no f prime. Once I take the derivative, then I write f prime. Over here, I'm still working on rewriting this on C right here, so I'm not writing f prime yet. I'm going to bring the half down. I still don't have natural log of x, and remember I need that. That's all I know. So, but this is multiplied, so I'm allowed to break that out. So f of x is still 1/2, and then it's be natural log of 2 plus natural log of x. Now I have a natural log of x by itself, and I'm allowed to take the derivative. So f prime is 1/2. What's the derivative of a constant? Natural log of 2 is just a number, that's gone. And what's the derivative of natural log of x? It's 1 over x, so I can do this, and I will call it a wrap. Okay, so we're done here. The last idea is just a reminder to you, I mentioned it earlier, but in order for a function to be differentiable, it must be continuous. Okay, don't forget that fact, and I will see you later.